Okay, good evening, everybody. It's Dr. Jensen, and we're going to start our second chapter dealing with atoms in the periodic table. All right, so our learning objectives for this chapter deal with three basic things. Okay, isotopes. All right, so we're going to talk about the periodic table, we're going to talk about elements, and importantly, out of that, we're going to talk about what isotopes are, and we're going to talk about the isotope designations. You should be able to identify the various parts of an isotope or the various elements based on what the isotope information gives you. Okay, we're going to talk about molecular weights. We're going to do some calculations with the molecular weight. Okay, so the molecular weight by itself is one thing that you should be able to calculate. So we're going to work with all kinds of molecules, and so you should be able to calculate the molecular weight of any molecule with the periodic table. Okay, you don't have to have this stuff on the periodic table memorized. Most people don't. So, but you should be able to calculate molecular weights given the periodic table. Okay, and one of the things that we do most with the molecular weight is to be able to convert between mass and moles. Okay, like density, molecular weight is a conversion factor between different terms. Right, so it's a relatively short chapter. So again, this is material for test number 1, where we are going to talk about, it's going to be chapters 2, 3, and 4. So this begins our conversation about the atoms. Again, the design of this course and some of the books that are done now are called Atoms First. And so we talk all about the atoms and quantum mechanics and molecular design and geometries, all these other things up front. So that way we know as much about the atom as possible before we start looking into the reactions of the atoms. All right, so this first part is simply just terms in history. There's nothing here that we're going to be quizzed on. It's mostly just being familiar with some of these things. So we have some background. So this is like in the last chapter, we looked at some basic vocabulary words that we'll use throughout the chapter. All right, so since early philosophers originally started talking about a fundamental particle or a fundamental element or some indivisible piece of matter that they believed existed, something that you couldn't divide things further into. So we've had these ideas for a long time of these very fundamental building. What is life made up of kind of stuff. So, again, these early philosophers were looking at, the basic elements were like earth, fire, water, and wind kind of thing. But they had a very rudimentary idea that, okay, well, we build houses with bricks, then there must be some kind of thing that is used to build other things, right? Some sort of initial particle. But they didn't really have any real idea of what they were talking about, not in a real sense. So a lot of it was just guessing about some of these phenomena without a way to experiment. So we've talked about Antoine Lavoisier. So again, he was kind of one of the first people who derived a lot of the basics that we need for this. So the law of conservation of mass really starts us off here. Okay, as the material that we have beforehand equals the material we have at the end. Okay, so in a closed container, the mass doesn't change of our reaction, right? So he looked at measuring a reaction, but it was all stoppered and everything inside his his reaction vessel. There was clearly a reaction that took place, but the mass remained the same after the reaction had taken place. So for us, we're not going to be as rudimentary to say mass, as in like the weight doesn't change, but we can look at the amount of matter. So we're going to talk about moles, right? Moles is our measure of matter, right? So when I have a log, right, I have a certain amount of carbon that's present, okay? We're going to measure the amount of carbon in moles, right? When I burn my log, obviously things change, right? It doesn't weigh the soot, the ash, and the gases and things like that. From a weight perspective, it's hard to imagine the the things adding up to the log that we started with. But the amount of stuff is the same. Okay, the carbon in the ash and the carbon in the gas would be the same amount of carbon in moles as was originally present. Joseph Proust looked at law of definite proportions. So this took it a step further to look at a molecule where if we look at water, it always has the same composition. Okay, if we change the composition, we change what it is, right? So H2O2 is not water. Okay, hydrogen peroxide is an entirely different molecule. It has different physical properties. It reacts and behaves differently. Okay, so essentially the law of definite proportions says is that a molecule will always maintain the same proportion of elements if it is in fact the same molecule, right? So all compounds all of the same compound will will have the same proportion. Right? So things push forward a little bit more. So we talked about John Dalton as one of the other fathers of modern chemistry. So in this case, Dalton derived what we now to understand to be the atom, okay? The fundamental building block, right? The smallest unit of an element, okay, that can participate in a chemical reaction, okay? Elements differ from one another, and so compounds are made up of at least two or more elements, okay? And we also look at whole number ratios. I can't have half of an oxygen atom. It must be a full atom of oxygen, okay? And that the atoms themselves are neither created nor destroyed during chemical reactions, but are changed in the process, okay? So a lot of these fundamental ideas, John Dalton brought these forward, that this makes some of our understanding of chemical reactions somewhat more, it doesn't necessarily have to be like understandable, but within a conceptual realm to where we can apply it to different things and that things begin to make more sense, at least in some way. Okay, obviously chemistry is still not easy, no matter what it is we're talking about. But if we understand the basics of the fact that there are whole numbers of elements, the moles of these things don't change, the ratio of the elements stay the same, it begins to frame in our universe to where it's not the wide expanse of everything we don't know. We begin to make boundaries of our information, that how we understand matter falls within these boundaries. Okay. So we also know, okay, there's a law of conservation of energy, right? That energy is conserved, that energy just changes form from one to another, okay? That the sun's energy is absorbed by plants, converted to other kinds of energy that we eat and convert that to motion, or our bodies give off the excess heat as well. And so it just goes through a cycle of changing from one form to another. Okay, so when we'll talk about the process of thermodynamics in another chapter. All right, and so what you see on the screen here, so what we have is a basic understanding that there were, right, elements and atoms. And so what Robert Brown, who he was a botanist, right? And so he was looking under a microscope, 1827, and saw particles of pollen moving around, okay? And so he didn't really understand what was causing the motion. Now, it wasn't until 1905 that Einstein mathematically modeled this motion that's now called Brownian motion, but it essentially demonstrates that there were particles or elements or atoms in the air bumping into the pollen grain, causing it to move. Right? That there were atoms and things around the pollen grain that we couldn't see. Okay, so amongst the many things that we understand Einstein was known for, demonstrating mathematically the existence of atoms, probably not one of the things that this is not one of our first things that we think of. Okay, so in an atom, okay, now these are basic things that most people are familiar with, at least in some regards. There are three basic particles of an atom. We have a proton, a neutron, and an electron. Okay, for our purposes, protons are going to be positively charged, electrons are negatively charged, and neutrons are neutral. Okay, so what we have in the atom is, now there's another unit here that you're going to see. It's called an angstrom. So the size of an element or an atom it's kind of an awkward number that you get. It's not quite, it doesn't quite work with nanometers, but it also doesn't quite work with picometers. And so we have 10 to the negative 9th is the nanometer, but we have 10 to the negative 12th is a picometer. So it is in kind of this weird space in between them where it's kind of too small for one unit and too large for the other unit. And so the angstrom is a 10 to the negative 10 unit. Okay, so in your metric system unit, right? So I would say that there are 10 to the 10th angstroms in 1 meter. Okay, so this essentially reframes the size of the atom in a 1 to 5 angstrom size. That we find that most atoms tend to be about 1 to 5 angstroms, and the nucleus, the center, is a relatively small space within the whole of the atom. Okay, now because we have positive and negative charges within an atom, we get interesting interactions. Okay, we get repulsion from like charges. Positives repel one another, negatives repel one another. Opposite charges attract each other. Positive and negatives are attracted to one another. And so we get this attraction and repulsion that naturally exists within atoms. So as soon as the fact that we even have positive and negatives, okay, their simple existence of opposite charges means that there will be, in some statistical amount, an attraction between molecules, which means from the universe, we will get molecules from atoms naturally. They will be attracted to one another and they will make other molecules naturally without any kind of intervention because of their opposite charges. Okay, just from the fact of having positives and negatives, you will get things attracted to one another. Okay, just like two magnets sticking together. Okay, it will happen regardless of what we want, just by putting them in contact with one another. All right. So in early looking at what the makeup of the atom was, okay, because again, Dalton just came up with the idea of the atom, the fundamental particle that was indivisible. But we still didn't know what it was or what it was made up of, right? And so J.J. Thomson was working with cathode ray tubes, okay? So it's basically a vacuum tube and with a battery attached to it. And so you get a cathode and anode. And so, this is how we get, various things like neon signs and things like that are in these cathode ray tubes, and old TVs utilize these as well. All right. And so what you can see is a magnetic field applied over this, this beam. We see a change in the beam's trajectory. Okay. Now, light is not affected by a magnet like that. So that means there must be something else there, right? And so I'm going to show you a video here. So hopefully my video will work here. Okay, so the fact that something exists, hang on. Yes, this lecture is being recorded and it's already, and it'll be on the Canvas site. So we can see that the light it's not light. There is a particle in there that is affected by the magnet. Okay, so the results of this experiment demonstrated that there was something there, and it was negatively charged. It was reacting to the presence of a magnetic field. Okay, and so this demonstrated the presence of electrons. Okay, what actually, I think the electron was originally called a corpuscle, right? So it's actually so we call them electrons now. So we know experimentally that there was a negative particle present. The electron charge and mass are not really important to us. The Coulomb charge there, again, we're just going to call an electron a -1. Okay, we're going to see an electron is -1. All right, so this Coulombic value is not really going to be important to us. All right. So as I said, Dalton's model of the atom was simply this spherical bubble, right? It didn't really have any notions that it was made up of anything, right? The idea was that it was an indivisible object, that there was no way to subdivide it, okay? So J.J. Thomson, though, with this cathode ray experiments, demonstrated that there was something there. There was an electron, there was a negative particle within the atom, right? And so he developed a refined model of the atom that he called his plum pudding model, right? So it's essentially like if you think of pudding, and if you just, you threw some, raisins or plums in there, that they would just be spackled kind of all around the pudding, right? You wouldn't end up with fruit like all on the right side of your pudding, or fruit all on the left side of your pudding, or anything like that. They were kind of all mixed up in there, right? And so it wasn't until later on that we have, Henry Becquerel and Marie Curie working on, obviously, radioactive materials, that other experiments were derived and designed in order to elucidate further the components of the atom. Okay, so through their experiments, obviously they discovered the various components of radioactive particles: alpha emission, beta emission, and gamma, right? So some of the goals were to try to refine how we understood the atom and what it was composed of, right? And so, like I said, the proposed idea from J.J. Thomson, again, that they were corpuscles, right? That it was this sea of uniform charges amongst the atom, and so that things were just kind of floating all in there like a big mixture of stuff. So Ernest Rutherford, who is known as the father of nuclear physics, was a student of J.J. Thomson's. And so his research further into radioactive materials, his goal in one of his experiments was to demonstrate and prove his advisors, his teachers, his mentors' model of the plum pudding model. Okay, so he derived an experiment, okay, where he took a radioactive substance and a very thin gold film. And so with this idea that you have an atom, that it is made up of all this dispersed space. If we took a high energy, but this radioactive source lets loose all kinds of emissions. So it's, it's got alpha, it's a helium atom, it's very big, it's got electrons, it's got gamma. But the point is that, if you are putting up one of those, those tennis ball machines, or, the batting cage machine, you set it up at home plate and you just start loading balls in there and you turn it to swivel like a fan and it's just shooting balls everywhere. If you got people just running around out in the field, the likelihood of them being hit by anything is slim to none, right? You're not going to hit anything with it because everything is all dispersed, right? And so what he found was all kinds of deflections that he didn't expect to see. Okay, so here's a look at the experiment. Okay, so the plum pudding model didn't account for how or why this would happen. Okay, so essentially what we have is a rejection of the hypothesis for the plum pudding model, that a new hypothesis or a new value had to be conceived of because it had failed the test. It had been proven wrong, that there was no way, because J.J. Thomson knew the size of an electron. He measured the mass of an electron. So there's no way, so Rutherford knew there was no way that an electron had enough mass to scatter an alpha particle. An alpha particle is a helium atom, okay, is a helium, okay? These are huge, okay? They're much, much bigger than an electron. It would be like, a bowling ball, a helium atom, going through electrons is like, shooting a 50 caliber, gun through mist, right? It's, you're not stopping anything, right? It would blow right through there. So, but there had to be something of significant size and charge that caused for a deflection. Okay, and so it was established that there were positively charged objects that counterbalance the negative, but that they were confined into an arrangement that put them in a nucleus. Okay, that put them at the center of the atom, and then put the electrons around it. That better matched the experimental design that we had seen. Okay, so here then we were able to measure the charge. So you see the charge is about the same as the electron, just the opposite. It's positively charged. It has a much larger mass. The electron was 10 to the negative 28, right? So we'll come back to their masses here in a second, right? So since atoms were neutral, right, they had to have, we already knew there had to be positive and negative. As soon as there was a negative, there had to be a positive. It's just that it was unclear how big the positive had to be, right? So this experiment elucidated that the positives were very big, that it was not a dispersed, field or cloud like the electrons. Okay. So we have some interpretations from his results. Okay, so this obviously changed the diagram of how the atom was seen, that there was a nucleus, okay, that brought a dense center, something that would have enough mass to reflect an alpha particle, right? The mass of the nucleus had to be sufficient enough again. So that's the weight of the protons had to be sufficient in weight, and it had to be positively charged. Okay, because we also see deflection from or bending from the beta particles, which are just electrons. So the problem became that now that we understand what these particles are, okay, and we're adding up, we can weigh atoms. Okay, we were using what's called an atomic mass unit as a weight, right? And it works fine at early or very small elements, hydrogen, helium. But when we get to beryllium, which we'll look at the periodic table here shortly, has 4 protons. So they assumed its atomic mass would be 4 AMU, but it's not. So if we already calculated the mass of the electrons, we already calculated the mass of the protons from very small atoms like hydrogen and helium, there had to be something else, right? If we eliminate the impossible or the possible, whatever is left over, however impossible, must be the answer. So in this case, we already know the electrons are positive, the protons or the electrons are negative, the protons are positive. We know their masses of both, but it doesn't add up to the total mass of the atom in some circumstances. So there must be something else. And in this case, they derived that there must be another particle that was neutral called a neutron, and that its mass was roughly about the size of a proton. Okay, slightly more than a proton. Okay, but you can't add another charge in there because that would disrupt the balance of charges, right? Because we already know the charge of the electron, we already know the charge of the proton, and we already know they're relatively the same charge. Okay. So we get all the components of the atom: proton, positively charged, neutron, neutral, and the electron, -1. Okay. So we're given mass units here, so you can see from looking at the mass unit. So the mass unit, we'll talk about the actual units that we're going to use here shortly, right? But you can look at the mass units now just from our first chapter. We know that if we're adding, right, if we're adding these 3 together, the fewer number of decimal places drives my answer, right? So if I'm adding my mass, right, here's my fewest number of decimal places, that the electron is virtually not adding anything to my mass of my atom. So when we look at the masses of the atoms, we basically can exclude the weight of the electrons. They are insignificant to the overall mass of the atom. Okay, that their size is too small. They don't weigh they don't add anything significantly to the mass. So most calculations for the mass of the atoms are done without the electrons. All right, so let's talk about the periodic table. Let's talk about these elements, right? Most elements have one or two letters for a symbol. So some elements are based on Latin names. So that's why we see like sodium is Na, because it's based on the Latin name natrium. Okay, some elements have only a single designation. Carbon has a C, sulfur is an S. Okay, we are generally designating that there is a capital first letter and a lowercase second letter. So this allows us to separate between things like cobalt as CO and carbon monoxide as CO, right? So it's cobalt is C little o and carbon monoxide is C capital O, big C, big O, okay? So elements come in all different kinds of shapes and forms, okay? If we look at carbon, okay, lots of people like to look at carbon, at least in some form fashion, right? Carbon we find in diamond as well as in the form of graphite, okay? Graphite and carbon are both the element carbon. They just have a different structure, okay? Germanium, sulfur. Sulfur is a very brittle metal. Sodium, again, is another, or sulfur is not a metal, sulfur is a non-metal, but we have it, but it becomes very brittle, right? And our sodium metal is very soft, right? So when we look at the periodic table, okay, so we're gonna have to get ourselves familiar with the periodic table here. All right, so when we look at the periodic table, I'll turn my video off here for a second. So when you look at the periodic table, as we're looking at it here, what you're gonna see is from the left side, okay, we have things like sodium. So you'll see the Na over here, sodium, potassium, rubidium, okay? And as we move this way across the periodic table, you'll get to kind of this brownish area here to where we have what are called semi-metals and then non-metals, okay? The non-metals are in the yellow and blue, okay? And they're generally organized, so most of the periodic table is made up of metals. So all of these are metals over here. And then we have kind of semi-metals as we transition into non-metals. Now, the periodic table has a variety, and this is, you know, when the elements were first being discovered, obviously this is things like where we see the scientific method at play here, the predictive ability of the periodic table. We knew that there had to be, like looking in the range here between zinc and arsenic, they knew there had to be elements in there. There had to be something that fit within those gaps, okay? We had an understanding that these elements existed, so there must be some gaps in between, right? And so, so these are pictures here, and I'm gonna mute my video again. So again, so our periodic table is not the only periodic table in existence. There were a variety of other kinds of periodic tables that people came up with. Now you can see these are two relatively kind of interesting designs for elements. Again, the goal here was to try to make sense of a variety of properties, okay? Looking at how they deal with electrons, how they deal with how they have chemical reactions similar to one another. And so there are energy properties that are also in there as well. And so we'll see this in the next chapter as we get into it. Our current periodic table, there are some limitations. When we look at things like trying to take into account all these different variables, it's kind of like, you know, again, if you think about like trying to group all the people in the class. Now, usually this example works a little better when you can see all the rest of your classmates, right? So if we try to group people in the classroom, right? Group people by maybe by gender, by hair color, by eye color, by height, or you know, any other kind of physical characteristics that we want to try and group people by. But you know, there's all these different variations that you may get. How do we begin to transition from, you know, people that are really tall with black hair to people who are maybe shorter with black hair, and you know, that don't have the same kind of, they have similar characteristics in the fact that they have black hair, but they're not similar in the fact that they have different heights. And so we have the same kind of thing for elements. We have a lot of different properties, how they react with one another. What kinds of energy patterns do they have? How many electrons do they give off? And things like that we have to account for that are difficult to do in a linear, square, blocky way, okay? And so that's what these early designs were meant to be, is to try and to demonstrate how can we organize the periodic table in a way that makes sense, that accounts for all of these different kinds of properties. Okay, and so you can see people took a variety of stabs at trying to organize the periodic table in a way that tried to represent some of their physical characteristics, some of their energy characteristics, some of their chemical characteristics, right? Until we get to kind of how we see the periodic table now, okay? So as I said, the periodic table is made up of mostly of metals. The division here in the green area, okay? So over here we have the metalloids, okay, our semi-metals. They have some properties of metals and some properties of non-metals. The yellow area here are our non-metals. They come in all different kinds of phases. You have solids, we have liquids, and we have gases. Most metals are pretty solid, right? Obviously, the one exception being things like mercury, right? So by metals, I mean basically what you expect of a metal. Right? We'll talk about things that are metallic properties, but essentially anytime we talk about metals, this is what we're talking about, is that they're shiny for the most part. They conduct heat, they conduct electricity, they're malleable, which means they can be shaped, they're ductile, they can be drawn into wires, they lose electrons, okay? So the loss of electrons is going to be the important property that we're going to come back to again, okay? And the fact that we can make pots and pans out of them is, and swords and stuff like that is not the important property that we're interested in, okay? The fact that they lose electrons is really going to be the important property we're going to come back to. All right, non-metals, as I said, we find them in all three states. Okay, we have solids in carbon and sulfur and phosphorus. We have liquids in things like bromine, and we have gases in things like chlorine and fluorine. Okay, and as you might expect, their properties are the opposite of the metals. They generally don't conduct heat very well. They don't conduct electricity very well. The solids like sulfur and carbon are very brittle. And importantly, for our things later, they gain electrons. Okay, the gain of electrons is going to be an important physical electrical property of the nonmetals that we'll come and talk about later. Okay, we have our semi-metals, right? Again, here, the semi-metals, they can be dull, but they can also be shiny. They could conduct heat and electricity, but maybe not as well as the metals. So they are generally good semiconductors. Generally, they're relatively malleable, sometimes usually ductile, and we also see some loss and gain of electrons. All right, our semi-metals are used in all kinds of things, and obviously the most important aspect of our metalloids are things like our computer technology. Okay, silicon, being a semi-metal, is exceptionally good at electron transfer, but is less on the heat transfer. So that obviously makes it ideal for things like computers, so we don't have to worry about, if we're putting energy into something, that it doesn't get too hot as a result of that. Okay, we use them in batteries, various other kinds of power cells. The green color of fireworks is due to boron. All right. So generally, we will look, when I draw the periodic table, you will see me draw it in a similar fashion to this, where we have these blocks, right? Where our main groups of elements here are in blue. This big section here in peach is our transition elements. So we'll talk a little bit about transition elements. Mostly in the next couple of chapters, we're going to focus on the main group, okay, the two blue parts. And we're not really going to talk about the lanthanide-naconite series for the most part. Okay. So as I said, most of the periodic table is made up of metals. So we have the nonmetals on the right-hand side and our metalloids that kind of provide a transition buffering zone as we transition from hard metal area into softer non-metal area. All right, so the modern periodic table is grouped into a couple of different ways, okay? So the columns are called families. The rows are called periods. Now, a family of elements is similar in some respects to like a regular family, is that they have similar traits or features to one another. So, maybe like everybody in your family has, dark hair and brown eyes, right? Versus, someone else's family that may have, more lighter skin and blue eyes, and your family is going to have similar traits to one another generationally, right? So an element family is going to react kind of the same way. So they have similar reaction in certain circumstances. Okay. So specifically, we're going to look at a couple of families here, the alkali metals and the alkali earth metals. We have some coin metals in here in the middle. That's the copper, silver, gold. We have halogens and noble gases. Okay, so these are some families that we're going to spend a little bit of time talking about. All right, so before we move any further, let's take a look at our poll here. On the right side of the periodic table, what do we expect to see? We find metals, transition metals, metalloids, nonmetals, alkali earth metals. What do we have on the right side of the periodic table? Okay. On the right side of the periodic table, what do you have over there on the right side? We should both have the same right-hand side, right? If we're all looking at the same screen, right? This website is Poll Everywhere. It is Poll Everywhere. The link is there at the top, is pollev.com/Sam Jensen 072. You can utilize this, like I said, it's handy if we download an app on your phone. This is very easy, and then you can just put in the Sam Jensen 072, and then it pops up when a poll becomes active. And in that way, we can have a little kind of discussion of a topic that we've just recently been talking about. Again, there's no points involved in this. This is mostly, like I said, I designed these or decided to try and use these during the last semester. I didn't get very far into it before we kind of all had the quarantine. It was meant to be more of like you work with your lab partner and you guys talk to one another and get to know each other and, talk about what you wanted to vote on. And then we'd come back and discuss after a minute or two. Okay, it looks like we are reaching a quorum on the nonmetals, which is the correct answer. On the right side of the periodic table, we have nonmetals. On the left side of the periodic table, or through most of the left side, are made up of metals, with our metalloids in the middle. So the metalloids are a transition from the metals to nonmetals on the right side of the periodic table. All right. So hydrogen is kind of its own element, is its own family. It is the most abundant element in the universe. It is important for all life. All of our carbon molecules have hydrogen in it. It is a nonmetal. It exists naturally as a diatomic gas, so it exists in nature as H2. There is no atom, hydrogen, as an element. It does not exist as hydrogen, H, by itself. It is H2 naturally. Okay. I said that first family, the alkali metals. Okay. Alkali metals, we see things like sodium and potassium and lithium. They are relatively soft metals for the most part. They are generally very reactive. You can see their flame test. So in sometimes in the lab, we would use a flame test to identify various metal compounds. They all tend to be very water soluble. All right. So here's another video. Okay. Now this is a pretty cool video. This is there is a fake version of this that I can show you later. That's a little more, I guess, theatric in its design. Okay, so see their chemical reactions are similar to one another. You saw a similar chemical reaction for each one of those metals, right? But it just became more reactive as they went down, right? The alkali earth metals, the next column over, so this is group 2A, they're generally a little harder, a little denser than the alkali metals. They're reactive, but generally a little less so than the alkali metals. They generally form soluble oxides. Right? What we see of the alkali earth metals, obviously calcium is a big one that makes up our bones and things, things in our muscles. We have, if you've ever, had to have an x-ray done of your intestines, they generally would have you drink this thick, chalky, white stuff that is a barium solution. So it's very dense, which allows the x-rays to then take a picture of your soft tissue. It's also used obviously in fireworks. Same thing with strontium. Magnesium is used in things like bolts and things. If we need a rather lightweight metal. Okay. Our halogens, going all the way over to our right side of the periodic table. Our halogens, our nonmetals, they all exist as a diatomic element. So that means they exist naturally as F2, Cl2, Br2, I2. So fluorine does not exist as F, okay? It only exists naturally as F2, okay? They are all very reactive. And we use them in all parts of, we use a lot of these elements naturally. So obviously we use, fluoride, okay? So this is one of the things on like the nomenclature where when we're spelling that so fluorine is the element, which we don't put, it's not fluorine in your toothpaste, it's a fluoride, right? It is an ion, right? And chlorine or chloride is generally an ionic salt that's used in swimming pools as far as bleach. It's usually a sodium hypochlorite solution. So it's usually not, so we generally don't use things like, straight chlorine unless you're like doing straight, solid waste refinement kind of stuff. So if you're over at the Blue Plains waste treatment plant, you probably find, pure chlorine gas or liquid chlorine that they use for sanitation. Again, fluorine is used primarily for, things like our teeth. It's naturally occurring in our water. So, I don't know why it is, but like still like we've, been fluorinating water for like, 60, 70 years now. And it's like, we still get people that crop up with, anti-fluorination, pseudoscience stuff. And it's ridiculous. It's, it's already in your water. It exists there naturally. The government doesn't have to put fluorine in your water. It's already there. So what we do is regulate the amount. So that way, if you're not using fluorinated toothpaste or taking fluorine mouthwash and things like that, that it improves our teeth. It also does things like cuts down on, things like our dental costs as a society of 350 million people. Bromine is used as an herbicide or insecticide. Iodine is a solution that they would swab on you before surgery. Normally it would be kind of this purplish solid that's sublime. So if we remember that word sublimation, that goes straight from a solid to a gas. And then our noble gases. So it's the very far right column. Each one of the noble gases, we'll talk about their noble properties in later chapters, but they generally are all gases at room temperature. They're very unreactive. They're practically inert. And this is due to their electronic properties that we'll talk about in the next chapter. Okay. So what I'm gonna do here is let's pause for a moment. Okay, so now we're gonna talk about elements and isotope designations. So we know that every element on the periodic table is unique in how many protons it has, okay? No two elements have the same number of protons, okay? If something has the same number of protons, it is the same element, okay? So we designate the number of protons as the atomic number. So it is often designated as Z, right? Or the atomic number, all right? So every element has a unique name or symbol, but every element can have different variations of neutrons. And when an element has a different number of neutrons, that changes its mass, okay? And so what we end up with are isotopes that are the same element, but different mass, okay? So if we have a carbon atom that has 6 protons and 6 neutrons, okay, that is going to be called carbon 12. But if it has 6 protons and 7 neutrons, then it's going to be carbon 13. It is the same element with a different mass. And so we designate the mass number as what we call A, which is the sum of the protons and the neutrons in the atom. Okay, so that's what's going to, again, the mass is predominantly looking at atomic mass units made up of neutrons and protons, right? And so this is the atomic symbol or isotope designation that you're only going to see in this chapter for right now, for these specific questions on this test, and then we won't use this again. Okay, at least not until you get to nuclear chemistry. Okay, when you get to the nuclear chemistry chapter in 112, or the second semester of chemistry, where we generally talk about nuclear reactions, the isotope designation will come back up. By then, you'll probably have forgotten most of the isotope designation, and you'll relearn this at that point. Okay, so the bottom number here, Z, is the atomic number, the number of protons. X here is designated as just what is the chemical symbol for the element. And A is the mass number, the number of protons and neutrons in the nucleus. Okay. And so here you have 3 different designations for these isotopes, okay? And so what you should be able to do would be, if I give you one of these designations, that you should be able to determine how many protons, neutrons, and electrons are present from the designation, okay? So A, okay, the element with the S is sulfur, okay? So 32 is its mass number, okay? So this designation here is slightly different, okay? So this one here is just the element and the mass number. So usually we use this when we talk about things like carbon 13, it's the element's name and the mass number. So cobalt 60, carbon 12, oxygen, 18. So we're giving the element and the mass number, all right? This is similar to B, where here we have fluorine 19, okay? The bottom number is missing, okay? Because it's always the same. It is the number of protons that the element has. So since that number doesn't change, at some point we stop mentioning it, right? So if we know uranium always has 92 protons, eventually we stop putting the 92 in there, okay? We have a periodic table. We can see how many protons it has. So the designations, so this is kind of superfluous information a lot of times, especially if you're on the test, you're gonna have a periodic table, okay? If you don't have one, I will give you one. But you're always going to have that. So you're going to know how many protons it has. So really the important number that you really need is the mass number. Okay, so sulfur has 32. So that is the sum of its protons and neutrons. So if we look at the periodic table, it has 16 protons. Okay, the protons are positive, the electrons are negative. So it's going to have an equal number of protons and electrons. Okay, because these are isotopes. These are not we're not dealing with charges. We're not dealing with charged species. So there is no difference in the protons and electrons. They are a neutral atom. So once you know the number of protons, you also know the number of electrons. Okay. Now how we find the neutrons is by subtracting the mass number. Okay. If this is protons and neutrons, if we subtract out the number of protons, we will be left over with the number of neutrons. Right. So 32 is the total mass minus the 16 protons gives me 16 neutrons. Okay. Fluorine, 19, has 9 protons. So 19 minus the 9 protons tells me I have 10 neutrons. Uranium, 238, has 92 protons. So 238 is the protons plus the neutrons. So if I subtract these two numbers, I'll be left with the number of neutrons. Okay, so from a designation, you should be able to break out these different parts. Okay, and again, this one here is looking at whether or not the symbol is right. Okay, so this is looking at whether or not it is written properly. Okay, so 14 protons on the bottom for a carbon is not correct. Okay, carbon has 6. Right, so these two are swapped. Okay, hydrogen doesn't have 2 protons. Nitrogen doesn't have 6 protons. Okay, sulfur doesn't have it has to have more than 6 protons. Okay, so this one's here is just being able to identify whether or not it's right or wrong. But for the most part, the previous slide is more what I'm looking for is can you pick apart the various parts? Okay, now eventually we will talk about ions. Okay, ions will be our main focus of where our chemistry is going to occur. Okay, when an atom loses or gains electrons, it will be called an ion. So so one of the physical properties that I just talked about for metals is that they lose electrons. So metals, 75% of the periodic table lose electrons, and when they lose electrons, they become positive. So they become what are called cations. Our nonmetals gain electrons, and so they are called anions. Now, generally, we put the charge in the upper right. So if there is a difference in charge, it will be designated in the upper right. Now, generally, you'll not see this whole conglomeration of designations. So generally, the isotope designation and the charge designation are not, we don't put all of this together. Okay, so this is merely for display on this slide rather than actual practical use of this information. Okay, so when we deal with ions, okay, we are less concerned with the neutrons, okay, because the ions, really the only difference are the difference between the protons and the electrons. Okay, as I said, the isotope designation is only useful in nuclear chemistry. It is not really useful to us for most of our chemical reactions that we're going to talk about. So you're going to use it for the one question, right? Or one or two questions maybe, but that's about it, right? The rest of the time, we're more interested in ions, okay? the positive negative difference is going to drive most of our chemistry that we're going to talk about, that we're interested in. Okay. So from the periodic table, we know that fluorine has 9 protons. So if it has a negative charge, that means it has gained an extra electron. Okay. Its charge is imbalanced. It has more electrons. Magnesium has normally 12 protons. As it loses 2 electrons, it loses and becomes positive. Okay, it's losing that negative charge. All right, so it loses, and as a +2, it has 10 electrons. Nitrogen here is -3. So normally it has 7 protons. If it's -3, that means it's gained extra electrons. W is tungsten. Okay, so tungsten normally has 74 protons, but if it is a +6, that means it has lost 6 of them. So we would subtract, and these were equal at one point. So it had 74 electrons at one point. After it loses 6, now it has 68 electrons. It's the difference between my protons and electrons to give the charge on the ion. All right, I meant to reset that one, so we'll come back to that one. We'll use that one next time. All right, so this slide here, so I want to jumpstart a few slides here because this will be something we'll finish up tomorrow. We'll finish up this tomorrow, but I want to highlight a few things that are going to be important that you will usually we are memorizing, right? As are the common charges on the elements. Okay, so for the nomenclature quiz, okay, the more elements you know, the more likely you get extra credit on the nomenclature quiz. Okay, the nomenclature quiz is only out of 30 points, but it has 50 total points possible. Okay, when we are putting elements together, one of the things that we are going to need, and we'll talk about nomenclature tomorrow, to know are the charges, because we have positive charges, we have negative charges, and when they go together, they have to balance each other. Okay, so I don't get an oxygen that's -2 with 1 sodium as +1. They don't work like that. It needs more sodium. It needs more sodium to balance those charges out. Okay, but if you don't know what oxygen's charge is, then it's hard to make the molecule when it comes down to that part. Okay, so we have to know a little bit about that. And so this is initially a little bit of memorization until we get to the next chapter. Okay, so it's just that you're looking at a couple of days before we get to that, right? So in the meantime, these are things that we should be memorizing until we get to the fundamental reason why is lithium +1? Why is sodium +1? Why is magnesium +2? Okay, so until we get to the why, these are things that we should be working on memorizing. Okay, you should know this information. Okay, you're going to need to know this information for the nomenclature quiz. Okay, the nomenclature quiz is separate. Okay, this is all in chapter 2, but these are separate questions from what's going to be on the test. Okay, now that being said, I will use nomenclature on the first test. Okay, so if I tell you that I have 50 grams of magnesium chloride, okay, how many moles is that? Well, the question is not about what is the formula of magnesium chloride, but if you don't know how to make the formula of magnesium chloride, you are not going to be able to come up with the number of moles, right? Because you can't do the molecular weight. Or if I ask, what is the molecular weight of magnesium bromide? If you don't know what the formula is of magnesium bromide, then you're not going to be able to calculate the molecular weight for magnesium bromide. Right? So these are some things that we need to start memorizing now, okay, along with elements. Okay, like I said, the first 20 elements is usually what the go-to rule. The first 20 elements, and then I'll give you another 10 on top of that are defined as the basic general chemistry first semester amount of elements that most everybody has some general requirement that you're familiar with. Okay, it doesn't matter really what chemistry class you take. In almost every chemistry class, there is some general amount of elements knowledge that we walk away with. Okay, that we have committed for at least some portion of the class. Okay, we will use the nomenclature for many other parts of the chapter. So a lot of this stuff builds on other stuff we're going to do. Okay. All right, so that's where we're going to stop for tonight.